There. Okay, welcome everybody. So thanks for coming. As you may know, yesterday was the day in which we celebrated women doing mathematics. So today I wanted to have a female speaker. So she is Gabriela Ovando from Universidad Nacional de Rosario. Thanks for accepting this invitation, Gabriela. She has a great commitment with the group of women doing mathematics. She's part of two gender committees, one of them in Argentina and the other one in Latin America. So we will speak about the geodesic flow on the groups. Thank you again, Gabriela.
Well, many thanks. Sorry. Many thanks for the invitation, Romina. Well, you will speak about some women working on geometry at the end of the seminar, and let me say that it's a pleasure for me to be here too, and I would like to speak about the geodesic flow on Lie groups. And if I have time, about the magnetic flow. So we start with the equations for geodesics. So in the general setting, we have a Riemannian or pseudo-Riemannian manifold. We have the Levi-Civita connection, and we know that a curve on M is a geodesic if it satisfies the equation 1. In the case of a Lie group, when we keep the Lie group with the left invariant metric, as usual, we write that the derivation of the curve can be written as the left translation of the curve on the Lie algebra that we write by x of t, and the condition of gamma being a geodesic is translated into an equation at the Lie algebra level, and this is x prime equals the transpose of the adjoint map on x evaluated on x. And this is called the Euler Equation. When we go to the tangent space, we can see how to rewrite those equations in terms of the tangent bundle. So we translate the equation of the geodesics before into the next one equation. So x prime equals b, and the Levi-Civita connection of x prime on b equals 0. And so when we go to a Lie group, we have the corresponding equations on the tangent bundle that you are reading there. And this gives rise to the known geodesic flow. So to study the geodesic flow, we will go to the symplectic framework. So as I said, I will fix the Lie group equipped with a left invariant metric. And so it is known that on the cotangent bundle of the Lie group, there is a canonical symplectic structure that you can induce to the tangent bundle with help of the left invariant metric. So the idea is you consider one form on the tangent bundle, this one form. Okay, first you trivialize the tangent bundle of n as n times the Lie algebra, and so general vectors are pairs on the tangent bundle. So the one form on the tangent bundle of a pair py evaluated on vectors on the pair of vectors u phi left invariant vector is equals the inner product of y with the vector u. Okay, so the symplectic structure you take on the tangent bundle is the differential of this one form. Well, when you have this setting, you define the Hamiltonian vector field associated to a function f by the formula at the end of the slide. Okay, it is implicitly defined by this formula, a formula which gives rise actually to two vectors. One is the Hamiltonian vector field, and the other one is the gradient vector field. So in terms, we will write the Hamiltonian vector denoted by xf in terms of the gradient vector field, because it is easier to, for me at least, to compute the gradient vector field, and so I get the formula for the Hamiltonian vector field in terms of the gradient field. And it is given by the next formulas. So if we denote the gradient field of f by the pair u phi v, the Hamiltonian vector field is given by the first formula you can read there. And so with this, you get for a given function f that you fix as your Hamiltonian, the corresponding equation, which is the equation for the trajectory of the Hamiltonian vector field xf. This is the general equation for a fixed Hamiltonian. For the setting for the geodesic flow, what we will have is the energy function. We fix as Hamiltonian the energy function. But first, in general, if you have the gradient equal u v, you have the corresponding Hamiltonian equation, and so for the energy function, you compute the gradient field. Here there is a mistake. This 0y is the gradient field, and the Hamiltonian equation is given at the end. The Hamiltonian equation for the energy function is given at the end of the slide, and you can see that this is the geodesic equation we had in the previous slide. It coincides with that one. On the tangent bundle. Okay, so with this framework, you get the geodesic equation for that. So now it is known that in general, when you have a symplectic structure, you can define a Poisson bracket on the set of differential functions on the tangent bundle. And this is given, so the Poisson bracket corresponds to the symplectic structure, which is applied to the pair of functions, to the pair of vector fields corresponding to the Hamiltonian vector fields for the function. So this expression, which is in equation 2, there u phi, u prime, and v prime are the corresponding components of the gradients of f and g. So we say that the pair function is an involution whenever the Poisson bracket is 0 and the notion of involution is equivalent by the definition we gave previously for the Hamiltonian vector fields corresponding to a function. This corresponds to the idea that the Hamiltonian vector field of one of the functions applied to the other function is 0. Okay, so it gives the idea of a derivative in some direction of the applied to the function that is 0. So the function should be constant along the trajectories of the vector field xg in this equation. And in general, we say that f is called a first integral if it Poisson commute with the energy function. Okay, so in terms with of the Hamiltonians and the components of the gradient of f, you get the formula given by the equation 3. Okay. Well, and one point is that the energy is always a first integral. Actually, the Poisson bracket is a Lie bracket with another property, extra property, but it's a Lie bracket. So it is skew-symmetric, and it is easy to see that the energy function is the first integral then. One extra definition is the definition of completely integrable in the sense of Liouville, when we have n first integrals with Poisson commute each with each other and that are functionally independent. That is, the gradients of the functions are linearly independent on an open dense subset of the tangent band. Well, complete integrability is not so easy to have, and there are some obstructions, topological obstructions, to get analytic first integrals. They were given by Kozlov, Taimanov, and in several papers, and there are other papers which speak about integrability and non-integrability. Well, let us give an example. Take the Heisenberg group with Lie algebra spanned by the bases x1, x2, z, such that we have the known Lie bracket, and take the metric that makes this an orthonormal basis. And we does the metric to the tangent bundle in such way that this is the product metric. Okay, so we take we take this metric on the Lie algebra, and we take the metric on the Lie group that makes this metric left invariant, and so we consider on Tn that we trivialize as n times the Lie algebra the product metric. So the left invariant metric on the Heisenberg group and the metric I said on the Lie algebra. Well, then if you take those functions, okay, you fix the energy function, that is a half of the inner product of y with y. Then you take this linear function, which is to take the component of the center of the vector y, and then you get g, another function g. You can compute and see that this is a set of commuting first integrals, which is functionally independent. Well, if you look at this function, you can think, well, it is easy. There is nothing too complicated there, because all these things seems to be polynomials, okay, in the coordinates of p and y. Actually, here this y is part of the coordinates of p. I am thinking that p has coordinate x, y, z. I didn't write that. But the point is, the question is when you take a quotient, okay? So you get, for instance, take a co-compact lattice on the Heisenberg group and consider the quotient. So you translate the left invariant metric on on the Heisenberg group, H3, to the compact quotient. So how can we induce the functions above to the quotient? So, well, the question is the last function. So now we will try to consider all the setting of the geodesic equation or the question of first complete integrability on the quotient. Okay. So when we try to translate the functions on the Heisenberg group, here the last function, to the quotient, you can see the first fz does not depend on the first component. Okay, the same holds for the energy function, but in the last case, for the function g, this is the question. So here in the function g, there is some part which depends on the coordinates of p. So when you try to bring this function g to the quotient, you should do something extra. Why? Because on the fiber, okay, this function g is not constant. Okay, so the point to translate this function g to the quotient is to do something by hand and to play a little with the relations you are able to work with respect to the Poisson bracket. So what we take is the function g, so we make the quotient by the function fz, and so we are able to eliminate in this way this part, and then, well, if you take the sine of 2 pi of this quotient, then you get a first integral on the quotient. A first integral that it is not analytic, but it is enough on the dense set in the tangent of the quotients on the manifold M. Okay, and this is so that you can do by hand when you try to get also complete integrability on the quotients. Well, I will not give many examples, but I wanted to show that to work on quotients is not so easy when you try to induce functions from the Lie group to the quotient. And what I know is doing by hand. All the definitions I was speaking are general for a symplectic manifold. For instance, another example of a symplectic manifold is given by the coadjoint orbits. On coadjoint orbits, you consider the known coadjoint action, and so you define a symplectic structure on the coadjoint orbits And so you fix also a function, and you define the Hamiltonian, and you define the Hamiltonian vector fields, and so on. So you can also study complete integrability for these other symplectic manifolds, okay, which are coadjoint orbits. The point is that coadjoint orbits on the Lie algebra do not have the same dimension. So you can have something different at each orbit. But there are a lot of theory given in this setting. Well, the question of Liouville integrability implies several things, and these are given in the Liouville theorem. So when you have a symplectic manifold and you fix a Hamiltonian, the Liouville integrability implies that on certain manifold that you can construct as the pre-image of a vector of a point C. You have a fixed description of this submanifold. For instance, so you take f1, fn, the n functions which are first integrals, or with Poisson commute with your Hamiltonian, and Poisson commute pairwise also. So with this first integrals, you define the function f. And so we take a C point and the pre-image of this point. So this pre-image MC is a submanifold of dimension n, which is Lagrangian with respect to the symplectic structure, and it is invariant by all the Hamiltonian vector fields corresponding to the functions fi. If MC is connected and compact, then it is diffeomorphic to a torus. Then also the foliation of Liouville is trivial in a neighborhood of the torus, and this means that it's diffeomorphic to a product Tn times the disk n, dn. And on this set, there are action angle variables, and this implies that the geodesic equation can be written in an easier way, okay, in terms of these action angle variables. Well, I will not speak much more about the Liouville theorem, but I would like to go to how to construct first integrals. So one of the settings to get first integrals is Killing vector. So once we have a Killing vector field on the manifold M, then it is known that a first integral can be given by taking the inner product of the Killing vector and the vector y on the tangent bundle. So in the case of Lie groups, the Killing vector fields are the right invariant vector fields corresponding to the translations on the left. When we consider, okay, so when we have the isometry group of a nilpotent Lie group with a left invariant metric, we know that the isometry group is a semi-direct product of the orthogonal automorphism of n and the Lie group n. Okay, the Lie group n corresponds to the invariant to the translations on the left, sorry, by elements of the group, and the corresponding Killing vector for the translation on the left are the right invariant vector fields. Okay, And this other part, the orthogonal automorphism, are determined by the derivation, the orthogonal derivation. So in the case of 2 and 3 step nilpotent Lie groups, we can prove that there is a monomorphism of Lie algebras from the Lie algebra of the isometry group, keep with its Lie bracket, to the set of first integrals, okay, or functions on the tangent bundle with the Poisson bracket. Okay, this is a homomorphism of Lie algebras, which is also injective. Well, the proof for this in the case of 2 or 3 step nilpotent Lie groups is given by hand by using the explicit formulas of the corresponding Killing vector fields. So, for instance, in the case of the skew-symmetric derivation, you get a formula for the Killing vector fields, and as you can see there, you have for the 2-step nilpotent case, you get a formula with 2 terms, which is the derivation applied on a vector minus a half of the Lie bracket, and in the case of the 3-step nilpotent Lie groups or Lie algebra, when you go to the Lie algebra, so you have these 3 terms inner product with Y. So I will not give the proof here, it is very technical, but you need to compute the derivations to get the formulas for the gradients, and then to compute the Hamiltonian for doing the Poisson bracket. And well, you are using indeed the structure of the isometry Lie algebra, which is given there as the it is the Lie algebra corresponding to this semi-direct product of the Lie groups I gave previously. This is part of the more general result given by Woodhouse in 75, which established that this is a homomorphism. The general situation is that here this homomorphism still holds in general for the isometry Lie algebra of given sending the Killing vector fields to the is an anti-homomorphism from the sending the vector fields to the corresponding first integrals. Okay. Well, this is the question or the setting for Killing vectors, and another family of first integrals is called invariant first integrals. Why? Here, what we call invariant is a function that satisfies the condition f in py equals f in the identity y. That means, okay, we have an action, natural action of the Lie group N on the tangent bundle by left translation. Okay, so we consider this action translation on the left, on the first, and on the second, and also on the second component. But on the second component, we take the formula for left invariant vector fields. So here we don't have any change by the action. And so we say that the function is invariant by this definition. So the energy function we are fixing here is invariant. And we have the following. If we take an invariant function, the gradient is easier, so it has no component on the first part. Okay, the first component is 0, and so the expression of the Hamiltonian vector is easier. It depends only on the second component here, v. When we have an invariant function, it is equivalent to have a function on the Lie algebra, actually, so which is given by the formula here. So a function on the tangent bundle give rise to a function on the Lie algebra by the formula f in py equals f in y. Okay, so the function on the left is on the tangent bundle, the f on the right is on the Lie algebra level. And so in this way, when you have that the functions are invariant, then the Poisson bracket is easier and reduces to the formula 4. Okay, then you, in the previous cases, you have 3 terms, and here for those functions, the Poisson bracket reduces to only to 1 term. Okay, and it depends on the Lie bracket of the gradients you have. Well, it is easy to see that if you get an invariant function, then it Poisson commute with the first integrals corresponding to the translations on the left. Okay? So, if we have this, it is nice to construct families of abelian first integrals. So actually the complete integrability means that you need to have an abelian subspace of first integrals. Okay. In the case of the theorem I told above, this of the monomorphism, by using this theorem, you can get complete integrability if you have a family of an abelian family. I will go back to this theorem here. So if you get a, what is the use of this theorem? The use is that if you have an abelian family here in the isometry Lie algebra, that is a subalgebra, an abelian subalgebra of dimension n, then you will have here with the corresponding function, you will have complete integrability. Okay, this is the use, but this is not so easy to have actually. But if you know the isometry Lie algebra, maybe you're able to have an abelian subalgebra here. And so you know by this theorem that you will get a family that will give you the complete integrability. Well, but if you don't have this abelian subalgebra of dimension n, then you need other first integrals, and for instance, those first integrals which are invariant will give you something more. Okay? For instance, by using the lemma, you take the first integrals corresponding to translations on the left, and you will have a commutativity with respect to the Poisson bracket. Okay? So the next part will be to try to get conditions on some invariant first integrals you can compute easily for being first integrals in general. Okay, so the first example is to get, for instance, linear first integrals. So linear first integrals, I mean, to define this easier function. If x of py is to take the coordinate of y with respect to x, that is to do the inner product of x and y. And so, if you ask which x you can take to have a first integral, the condition is that the atom at x should be skew-symmetric with respect to the inner product. Now, another kind of first integrals you can have are of the form of the functions gs. So you take a symmetric endomorphism of the Lie algebra, and you do the inner product of y with sy, and so you get a quadratic function on the coordinates of y. Okay, it's a quadratic polynomial. So the condition of being a first integral is translated in equation 5. So when you try to get more first integrals, you can do or find more if you have this. For instance, in the condition of at x of being skew-symmetric, in the case of a nilpotent Lie algebra, implies that x should be in the center of on the Lie algebra. Okay. And so what we can have also is all the involution conditions. So when we have involution between linear function, if v, okay, so the condition is that these are in involution if and only if the Lie bracket of u and v is 0. When we have Poisson commutativity between fu and gs, where gs correspond to a symmetric map, well, the condition is that they Poisson commute if and only if at u composed with s is skew-symmetric. And finally, the other condition, when we have two symmetric maps, and we get the corresponding first integrals as above, we get the Poisson commutativity if and only if we have this condition, the inner product of y with the Lie bracket of sy and ty should be 0 for all y in the Lie bracket, in the Lie algebra. Okay, and in any case, you should compute all the things. And in the case that the Lie algebra is a nilpotent Lie algebra, which is chi-step with k equal 2 or 3, then you have conditions for the Poisson commutativity corresponding to, here T is skew-symmetric derivation. So this is the Killing vector corresponding to an element of a skew-symmetric derivation. So with the linear map fu, so Poisson commutativity here is equivalent to u is in the kernel of D. And in the second case, also for a skew-symmetric derivation D, Poisson commutativity with a function gs gives that the linear map ds should be skew-symmetric. Okay. Well, in the two-step nilpotent case, you can specialize the condition for a symmetric map S to give rise to a first integral. For doing this, we make use of some known information on two-step nilpotent Lie algebras. This is given by using the decomposition of the Lie algebra in terms of the center and the orthogonal subspace V. Okay, so the condition of being two-step nilpotent says that the commutator is contained in the center. And Del Barco and Moroyanu gave a condition, an explicit condition for a symmetric map S to give rise to a first integral. And this is given in the conditions 1 and 2. You can read there. So the condition says that the Lie bracket of Sx with y should be equal to the Lie bracket of x with sy, and also that the map at x composed with S restricted to the center should be skew-symmetric for any x on the subspace V. So when we try to do something similar for the three-step nilpotent case, we will also get some conditions. But firstly, we will consider those functions, gi, which are also invariant. These functions were introduced by Butler. And well, we can compute also the conditions on the integrability and Poisson commutativity with all the other cases we consider above. Okay, the point is that these functions gi and gk, say when you vary I and k, they Poisson commute each other. So what you need is to consider the Poisson commutativity with the other functions, with the symmetric maps and so on, the linear maps and all the other cases. And the point is that these functions gi will give you polynomials of different degrees. Okay, when you increase the I, you will increase the degree of the polynomial you will have for gi. One. They were used in different examples for constructed families that give complete integrability in some cases. And these functions are defined only for the two-step nilpotent cases. Okay. Well, as I say, in the case of the three-step nilpotent Lie algebras, what you get, what you should consider is the composition on by considering the commutator and the orthogonal complement of the commutator. And so by writing the condition of a symmetric map S to give rise to a first integral, you get these three conditions there. Okay, the first one is similar to that one in the two-step nilpotent case, but the second and the third one are a little different to those written in the two-step nilpotent case. Okay. Well, some applications. So all these tools help you to prove the following theorem, that in dimension 5, okay, or 5, actually 3, 4, and 5, for any k-step nilpotent group with k equals 2 or 3, there is a left invariant metric whose geodesic flow is Liouville integrability. And the proof follows by a case study. So here is the list of Lie algebras you have. And at the right, you will have all cases, all first integrals that had to use to prove the complete integrability. Until now, for proving complete integrability in the two-step nilpotent case, we were using actually only the Killing vector corresponding to translations on the left. And here, as you can see, the Lie algebra N3, okay, it appears a first integral corresponding to skew-symmetric derivation. And this Lie algebra is a three-step nilpotent. So that means actually that with previous tools, that is Killing vectors corresponding only to translations on the left, or symmetric maps or linear maps and so on, you were not able to prove complete integrability. In this situation, we needed to consider the part of the isometry group corresponding to orthogonal automorphism. That was one motivation to study the three-step nilpotent case. In dimension 6, we were able also to prove complete integrability, except in two cases, and this was also given by a case study and by using the list of the graph of classification of nilpotent Lie algebras in dimension 6. So some questions that we can put here is, well, how to induce those first integrals to quotients. As I show in the case of the Heisenberg group, it is not so easy to induce the functions to the quotients. But the point is that even if it is not easy to induce these first integrals, we are not able to know if the geodesic flow is integrable or not. Okay, so this, in some sense, will ask if we can say something about integrability or non-integrability. What does it mean, non-integrability or integrability of the geodesic flow? There are a book of Fomenko about non-integrability, but I think it is not so good understood until now. What does it mean for compact quotients? I don't know if I have some more time.
Yes, you have. Yeah, you have some minutes.
Some minutes?
Yeah, no, a lot of minutes. Because a lot of minutes.
Well, any question until here? Because I will go to another, to the magnetic flow, maybe. No? Okay. Well, so here is maybe another equation of the. I was starting to try to generalize some of this setting I was speaking about for magnetic trajectories. So we are in a similar setting as before. So we have a Riemannian or pseudo-Riemannian manifold, okay? And now we take a skew-symmetric linear bundle map, okay? And so we say that the curve is called a magnetic trajectory if it satisfies the equation 11, Okay. In physics, this equation is called the Lorentz equation, and it describes the behavior of a particle under the action of a Lorentz force, or magnetic field is also called. Well, I was looking for mathematician working on magnetic flows, and I think one of the first paper I found was of Tsunada in 1993, where he was working on a Riemannian surface showing that a magnetic flow on a hyperbolic surface with the strength smaller or equal than 1 is anosov, or respectively, or cycle flow. While in the other case, it's periodic, provided the strength is greater than 1. So you can there have a classification and a description in all cases. And there are several works of Adachi of scalar magnetic flows on complex projective spaces, on manifolds of constant holomorphic sectional curvature, and negative curvature, etc. And there also Jamil Godoy and Marco Salvay work the magnetic flow on the manifold of oriented geodesics on a three-dimensional space form. So some example to consider in the previous case is, for instance, to take J, an almost complex structure, okay, and to ask the corresponding scalar form to be closed. This is called an almost scalar structure on the manifold. The magnetic field is uniform if it is parallel with respect to the Levi-Civita connection, okay? So in the case that J is an almost complex structure, the condition of being parallel J gives a scalar structure on the manifold. Well, here in the next paragraphs, you have some features that were obtained by Adachi. Okay, he was able to describe magnetic trajectories on the complex space, on the projective space, and also on the hyperbolic spaces. Okay, so you can go to the works of Adachi from 94 till now. I think he is working on this with scalar magnetic fields, actually. And there are also many works of the magnetic trajectories or magnetic geodesics on homogeneous manifolds by Magatsev, by Jovanovic, Bolsinov, Zorka, actually they are working most on quaternion orbits on semi-simple algebras. Okay, the point of working on semi-simple algebras is that when you know that you have the Killing form, and when you have an ad-invariant metric, then the coadjoint orbits are equivalent to the adjoint orbits. So you can translate all the setting at the Lie algebra level, and so they are working with some kind of decomposition and using much more of the Lie theory to prove several results on this context. But I think there are not so many things done in the case of solvable or nilpotent works. Okay, Patterson and Burns, they work on dynamical systems, so they are trying with the ergodicity and entropy. Actually, most of the questions on these things are about entropy and so on, and as a dynamical system for the equation. Now, how we shall work this equation in the setting when we work with a symplectic setting. So when we have the magnetic equation at the Lie group, so we do the same as in the case of the geodesic equation, and so we have the magnetic equation at the Lie algebra level, okay? And this equation is that what you are reading at the first equation, okay? Formally, the magnetic field is determined by a closed two-form on the manifold, okay? So generally, on the Lie group, and you take a map J, which is skew symmetric, and you take the associated to form, which is given by the second formula there. So if you assume that it is closed, then we define a two form on the tangent bundle by adding to the previous canonical symplectic structure on the tangent bundle the pullback of the two form on M, okay, that I call omega J, okay. So the second term modifies the canonical symplectic structure on the tangent bundle. This new symplectic structure was called the twisted symplectic structure by Arrow. Well, and now you can do the same as above. So you fix the vector field function, and you define the Hamiltonian vector field corresponding to the function f, okay, by this formula, now with respect to the symplectic structure omega j. And for the magnetic equation, so to get the magnetic equation, what we fix is also the energy function. So you fix the energy function. As we know, the gradient of the energy function is 0y. And so we get the Hamiltonian vector field now with respect to the symplectic structure omega j. And we get the next formula. The formula 12, p prime equals y, y prime equals the transpose of the adjoint map of y in y plus q jy. So more generally, if the gradient has components u and v, then by computing we get this formula for the Hamiltonian, for the corresponding Hamiltonian vector field. And also we define the Poisson bracket of two functions f and g, okay, by also doing the symplectic structure g on the corresponding Hamiltonian vector fields. So the formula now, you can see the formula there previous to the equation 13 is very similar to the formula we had in the case of the geodesic equation. Actually, it's the same thing. There are some differences here in the last plus, and here we have another term which corresponds to the J, to the map, to the skew symmetric map. Okay, so in some sense, this new Poisson bracket is a modification of the Poisson bracket we had in the other situation by considering the canonical symplectic structure on the tangent bundle. And now we have a new condition for a function f to be a first integral, okay? And this is in equation 13. Well, in the previous case, we didn't have the last term. Okay, for a geodesic, for the case of the energy function with the canonical symplectic structure, we should erase the last term. Okay. In the case of invariant functions, we also have a condition as previous. We define invariant functions as before, okay? Functions which are invariant by the action on the left of the Lie group. And so we were trying to work or to find conditions for getting first integrals with respect to the new symplectic structure. And, well, we can ask all the things we asked previously. Which kind of linear maps would be first integrals? And so you get a similar condition as before, plus one term, and this says that a linear function is a first integral if and only if the adjoint map of the vector is skew-symmetric, and also that the vector should be in the kernel of the skew-symmetric map. After that, you can consider also a symmetric map and to ask if in which situation this map that you can construct with the symmetric map is the first integral, and so you get the formula you are reading there, and this formula translates into two conditions. The first one is as in the case is the same as in the geodesic flow, and you get an extra condition which says that the map J should commute with S. And well, I think this is most I was able to compute in this case of the magnetic flow. And there are several questions in the case of the magnetic flow. I was not able to construct to give an example of the complete integrability because I was working on this until now. And a question for me is how to generalize the Killing vector for the setting of the magnetic flow. I do not find until now a vector for, like in the case of the geodesic flow, which play the role of the Killing vector field. How to define some kind of new vector that will give the Poisson commutativity as gave the corresponding first integral for the Killing vector field, but now in the case of the magnetic field. Well, that is all I have for today. Thank you.
Thank you, Gabriela. Is there any question or comment for Gabriela? Is there any question, Joe? Are you speaking?
Can I ask a question?
Yeah.
Sorry. No, about the last magnetic flow, did you, for instance, what happens in the Heisenberg algebra? Do you have solutions for these symmetric maps?
Not in the general case. I was trying only in dimension 3, And there you have only one possibility for the symmetric map, which is the energy function. That is to consider only the identity, actually. But I didn't try in higher dimension. You should fix the J. I didn't write many equations with J, but in the Heisenberg-Lie group, dimension 3, so you should, I think you should take something like almost complex structure, but in dimension 2, and then to have a kernel for having something non-trivial. And
is there a condition for the J? Is any?
It's only skew symmetric.
Okay.
Only skew symmetric. So it could have a kernel. In actually in.
But you don't put any other condition for J. First, only skew symmetric on the Lie algebra. That's
only skew symmetric, and the condition that the associated symplectic form should be closed. This is a condition I didn't write, but this is the only thing you need to do the theory. Yeah.
Okay, interesting. Thanks.
Is there any other question or comment? So I have a question, but I have a question about the first part of the talk regarding the dimensions. What happened with dimension 7? So are there any results, or the problem is that there you have cubes of the algebras?
Well, when I was looking for results, I started in dimension 5. I was able to prove complete integrability, and in dimension 6, no. So I have two cases in dimension. So I didn't follow with dimension 7, because for me it's already a question in dimension 6 that I have two algebras of the list that I was not able to prove complete integrability. I don't know how.
Okay, but okay, I didn't understand that. So though these two exceptions are because you cannot. But
I was not able complete integrability, but I don't know if there are integral or non-integral. That is, I fixed a metric, and I was not able to construct enough first integrals. You need 6 first integrals in those cases with the techniques I speak above. So this was the problem. I don't have another example, another theory to construct more integrals.
Okay.
So.
Okay, thank you. Is there
in dimension 7? So yes.
Yeah. Is there any other question for Gabriela? Well, if not, let's thanks again, Gabriela. Thank you, Gabi. And now I would like to share one picture to finish this seminar. So in this picture, you can see a lot of women. So these are our women. So all of them are or were professors, postdocs, students, or students of members of our group. So I wanted to thank all of them, because most of them were part of my career, my short career. So thank you, all of them. And I don't know if someone wants to say something, but I wanted to finish the seminar with this picture.
Maybe you should give the names. I don't know if all people know the.
So in order, so we have Isabel Dotti, Josefina Renuevo, Cynthia Will. I forgot the name.
Miriam Pacheco. Miriam
Pacheco, Cecilia Herrera, Diana Farías, Camila Molina, Gabriela Ovando, María Laura Barberis, Vanina Nicolini, Josefina Drueta, Yamile Godoy, Viviana El Barco, Valeria Gutiérrez, esta la sabés vos, Gaby.
Eleonora Siriza.
Siriza, Sonia Vera, María Alejandra Álvarez, Verónica Díaz,
Alicia García.
Anaíta, Amelia Barrio Nuevo, Daniela. Paola Manuel y Ana Carolina Pérez.
Muy lindas fotos.
Gracias. I'm not sure if I miss, I hope not to miss anyone.